IBM PC compatible computers are those similar to the original IBM PC, XT, and AT and able to run the same software as those. Such computers used to be referred to as PC clones, or IBM clones. They duplicate almost exactly all the significant features of the PC architecture, facilitated by IBM's choice of commodity hardware components and various manufacturers' ability to reverse engineer the BIOS firmware using a clean room design technique. Columbia Data Products built the first clone of the IBM personal computer by a clean room implementation of its BIOS. Early IBM PC compatibles used the same computer bus as the original PC and AT models. The IBM AT compatible bus was later named the industry standard architecture bus by manufacturers of compatible computers. The term IBM PC compatible is now a historical description only, since IBM has ended its personal computer sales. Descendants of the IBM PC compatibles comprise the majority of personal computers on the market presently, although interoperability with the bus structure and peripherals of the original PC architecture may be limited or non-existent. Origins. IBM decided in 1980 to market a low-cost single-user computer as quickly as possible in response to Apple Computer's success in the burgeoning microcomputer market. On August 12, 1981, the first IBM PC went on sale. There were 3 operating systems available for it. The least expensive and most popular was PC-DOS made by Microsoft. In a crucial concession, IBM's agreement allowed Microsoft to sell its own version, MS-DOS, for non-IBM computers. The only component of the original PC architecture exclusive to IBM was the BIOS. IBM at first asked developers to avoid writing software that addressed the computer's hardware directly, and to instead use the BIOS. Software which directly addressed the hardware instead of making standard calls was faster, however. This was particularly relevant to games. The IBM PC was sold in high enough volumes to justify writing software specifically for it, and this encouraged other manufacturers to produce machines which could use the same programs, expansion cards, and peripherals as the PC. The 808X computer marketplace rapidly excluded all machines which were not functionally very similar to the PC. The 640 kilobytes barrier on conventional system memory available to MS-DOS is a legacy of that period. Other non-clone machines did not have this limit. Rumors of look-alike, compatible computers, created without IBM's approval, began almost immediately after the IBM PC's release. By June 1983, PC Magazine defined PC clone as a computer that can accommodate the user who takes a disk home from an IBM PC, walks across the room, and plugs it into the foreign machine. Because of a shortage of IBM PCs that year, many customers purchased clones instead. Columbia Data Products produced the first computer more or less compatible to the IBM PC standard during June 1982, soon followed by Eagle Computer. Compaq announced its first IBM PC compatible in November 1982, the Compaq Portable. The Compaq was the first sewing machine-sized portable computer that was essentially 100% PC compatible. The company could not copy the BIOS directly as a result of the court decision in Apple v. Franklin, but it could reverse engineer the IBM BIOS and then write its own BIOS using clean room design. Compatibility issues. At the same time, many manufacturers such as Xerox, Hewlett-Packard, Digital Equipment Corporation, Sanyo, Texas Instruments, Tulip, Wang and Olivetti introduced personal computers that were MS-DOS compatible, but not completely software or hardware compatible with the IBM PC. Like IBM, Microsoft's intention was that application writers would write to the application programming interfaces in MS-DOS or the firmware BIOS, and that this would form what would now be termed a hardware abstraction layer. Each computer would have its own original equipment manufacturer version of MS-DOS, customized to its hardware. Any software written for MS-DOS would operate on any MS-DOS computer, despite variations in hardware design. This expectation seemed reasonable in the computer marketplace of the time. Until then, Microsoft was based primarily on computer languages such as BASIC. The established small system operating software was CPM from Digital Research, which was in use both at the hobbyist level and by the more professional of those using microcomputers. To achieve such widespread use, and thus make the product viable economically, the OS had to operate across a range of machines from different vendors that had widely varying hardware. Those customers who needed other applications than the starter programs could reasonably expect publishers to offer their products for a variety of computers, on suitable media for each. Microsoft's competing OS was intended initially to operate on a similar varied spectrum of hardware, although all based on the AT86 processor. Thus, MS-DOS was for several years sold only as an OEM product. There was no Microsoft-branded MS-DOS. MS-DOS could not be purchased directly from Microsoft, and each OEM release was packaged with the trade dress of the given PC vendor. Malfunctions were to be reported to the OEM, not to Microsoft. However, as compatibles became widespread, it soon became clear that the OEM versions of MS-DOS were virtually identical, except perhaps for the provision of a few utility programs. MS-DOS provided adequate functionality for character-oriented applications such as those that could have been implemented on a text-only terminal. Had the bulk of commercially important software been of this nature, low-level hardware compatibility might not have mattered. However, in order to provide maximum performance and leverage hardware features, PC applications quickly developed beyond the simple terminal applications that MS-DOS supported directly. Spreadsheets, WYSIWYG word processors, presentation software and remote communication software established new markets that exploited the PC's strengths, but required capabilities beyond what MS-DOS provided. Thus, from very early in the development of the MS-DOS software environment, many significant commercial software products were written directly to the hardware. For a variety of reasons, MS-DOS itself did not provide any way to position the text cursor. While the BIOS video interface routines were adequate for rudimentary output, they were inefficient. They did not have string output and they inserted delay periods to compensate for CGA hardware snow, an especially bad artifact since they were called by IRQs, thus making multitasking very difficult. A program that wrote directly to video memory could achieve output rates 5 to 20 times faster than making standard calls to the BIOS in MS-DOS. Turbo Pascal used this technique from its earliest versions. Graphics capability was not taken seriously in the original IBM design brief. Graphics were considered only from the perspective of generating static business graphics such as charts and graphs. MS-DOS did not have an API for graphics, and the BIOS only included the most rudimentary of graphics functions. To make a BIOS call for every point drawn or modified also increased overhead considerably, making the BIOS interface notoriously slow. Because of this, line drawing, arc drawing, and blitting had to be performed by the application to achieve acceptable speed, which was usually done by bypassing the BIOS and accessing video memory directly. Video games, even early ones, mostly required a true graphics mode. They also performed any machine-dependent trick the programmers could think of in order to gain speed. Though initially the major market for the PC was for business applications, games capability became an important factor motivating PC purchases as prices decreased. The availability and quality of games could mean the difference between the purchase of a PC compatible or a different platform like the Amiga. Communications software directly accessed the UART serial port chip, because the MS-DOS API and the BIOS did not provide full support and was too slow to keep up with hardware which could transfer data at 19,200 bits. Even for standard business applications, speed of execution was a significant competitive advantage. Integrated software Context MBA preceded Lotus 1-2-3 to market and included more functions. Context MBA was written in UCSDP system, making it very portable but too slow to be truly usable on a PC. 1-2-3 was written in x86 assembly language and performed some machine-dependent tricks. It was so much faster that it quickly surpassed Context MBA's sales. Disk copy protection schemes, in common use at the time, worked by reading non-standard data patterns on the diskette to verify originality. These patterns were impossible to detect using standard DOS or BIOS calls, so direct access to the disk controller hardware was necessary for the protection to work. Some software checked for evidence of a genuine IBM BIOS, such as an IBM copyright notice. During development, Compaq engineers found that Microsoft Flight Simulator would not run because of what Sublogic's Bruce R. Twike described as a bug in one of Intel's chips, forcing them to make their new computer bug-compatible with the IBM PC. At first, few clones other than Compaq's offered truly full compatibility. When PC Magazine requested samples from computer manufacturers that claimed to produce PC compatibles for an April 1984 review, 14 of 31 declined. Corona Data Systems specified that our systems run all software that conforms to IBM PC programming standards. And the most popular software DOS. When a Byte journalist asked to test eArcText at the spring 1983 Comdex, Corona representatives hemmed and hawed a bit, but they finally let me off in the corner where no one would see it should it fail. The magazine reported that their hesitancy was unnecessary. The disk booted up without a problem. Creative Computing in 1985 stated, "We reiterate our standard line regarding the IBM PC compatibles, try the package you want to use before you buy the computer." Companies modified their computers' BIOS to work with newly discovered incompatible applications, and reviewers and users developed stress tests to measure compatibility. By 1984 the ability to operate Lotus 1-2-3 and Flight Simulator became the standard. IBM believed that some companies such as Eagle, Corona, and Handwell infringed on its copyright, and after Apple Computer, Incorporated v. Franklin Computer Corporation successfully forced the clone makers to stop using the BIOS. The Phoenix BIOS in 1984, however, and similar products such as AMI BIOS, permitted computer makers to legally build essentially 100% compatible clones without having to reverse engineer the PC BIOS themselves. A September 1985 InfoWorld chart listed 7 compatibles with 256 KB RAM, 2 disk drives, and monochrome monitors for $1,495 to $2,320, while the equivalent IBM PC cost $2,820. The decreasing influence of IBM. As the IBM PC market grew, IBM's influence diminished. In November 1985 PC Magazine stated, "Now that it has created the PC market, the market doesn't necessarily need IBM for the machines. It may depend on IBM to set standards and to develop higher performance machines, but IBM had better conform to existing standards so as to not hurt users." In January 1987 Byte wrote of rumors that IBM would introduce proprietary personal computers with a proprietary operating system. Who cares? If IBM does it, they will most likely just isolate themselves from the largest marketplace, in which they really can't compete anymore anyway. The magazine predicted that in 1987 the market will complete its transition from an IBM standard to an Intel expansion bus standard. Folks aren't so much concerned about IBM compatibility as they are about Lotus 1-2-3 compatibility. By 1988 Gartner Group estimated that the public purchased 1.5 clones for every IBM PC. After 1987, IBM PC compatibles dominated both the home and business markets of commodity computers, with other notable alternative architectures being used in niche markets, like the Macintosh computers offered by Apple Incorporated and used mainly for desktop publishing at the time, the aging 8-bit Commodore 64, which was selling for $150 by this time and became the world's best-selling computer, the 32-bit Commodore Amiga line used for television and video production, and the 32-bit Atari ST used by the music industry. However, IBM itself lost the main role in the market for IBM PC compatibles by 1990. A few events in retrospect are important: the 1982 introduction of the Compaq Portable, the first 100% IBM PC compatible computer, providing portability unavailable from IBM at the time. An independent business unit within IBM developed the IBM PC and XT. IBUs did not share in corporate R&D expense. After the IBU became the entry systems division, it lost this benefit, greatly decreasing margins. The availability by 1986 of sub-$1,000 Turbo XT PC XT compatibles, including early offerings from Dell Computer, reducing demand for IBM's models. It was possible to buy 2 of these generic systems for less than the cost of one IBM-branded PC AT, and many companies did just that. Compaq beating IBM to market during 1986 with Compaq Desk Pro 386, the first 80386-based PC. IBM's 1987 introduction of the incompatible and proprietary microchannel architecture computer bus, for its personal system/2 line. The 1988 introduction by the Gang of 9 companies of a rival bus, extended industry standard architecture, intended to compete with, rather than copy, MCA. The dueling expanded memory and extended memory standards of the late 1980s, both developed without input from IBM. Despite popularity of its ThinkPad set of laptop PCs, IBM finally relinquished its role as a PC manufacturer during April 2005, when it sold its consumer PC division to Lenovo for $1.75 billion. As of October 2007, Hewlett-Packard and Dell have the largest shares of the PC market in North America. They are also successful overseas, with Acer, Lenovo, and Toshiba also notable. Worldwide, a huge number of PCs are white box systems assembled by myriad local systems builders. Despite advances of computer technology, all current IBM PC compatibles remain very much compatible with the original IBM PC computers, although most of the components implement the compatibility in special backward compatibility modes used only during a system boot. It is often more practical to run old software on a modern system using an emulator rather than relying on these features. Expandability. One of the strengths of the PC-compatible design is its modular hardware design. End users could readily upgrade peripherals and, to some degree, processor and memory without modifying the computer's motherboard or replacing the whole computer, as was the case with many of the microcomputers of the time. However, as processor speed and memory width increased, the limits of the original XT-AT bus design were soon reached, particularly when driving graphics video cards. IBM did introduce an upgraded bus in the IBM PS/2 computer that overcame many of the technical limits of the XT-AT bus, but this was rarely used as the basis for IBM-compatible computers since it required license payments to IBM both for the PS/2 bus and any prior AT bus designs produced by the company seeking a license. This was unpopular with hardware manufacturers, and several competing bus standards were developed by consortiums, with more agreeable license terms. Various attempts to standardize the interfaces were made, but in practice, many of these attempts were either flawed or ignored. Even so, there were many expansion options, and despite the confusion of its users, the PC-compatible design advanced much faster than other competing designs of the time, even if only because of its market dominance. IBM PC-compatible becomes Wintel. During the 1990s, IBM's influence on PC architecture started to decline. An IBM brand PC became the exception rather than the rule. Instead of placing importance on compatibility with the IBM PC, vendors began to emphasize compatibility with Windows. In 1993, a version of Windows NT was released that could operate on processors other than the x86 set. While it required that applications be recompiled, which most developers did not do, its hardware independence was used for Silicon Graphics x86 workstations. Thanks to NT's hardware abstraction layer, they could operate NT. No mass-market personal computer hardware vendor dared to be incompatible with the latest version of Windows, and Microsoft's annual WinHEC conferences provided a setting in which Microsoft could lobby for and in some cases dictate the pace and direction of the hardware of the PC industry. Microsoft and Intel had become so important to the ongoing development of PC hardware that industry writers began using the portmanteau word Wintel to refer to the combined hardware-software system. This terminology itself is becoming a misnomer, as Intel has lost absolute control over the direction of x86 hardware development with AMD's 64 Armenian DRAMs. Also, non-Windows operating systems like Mac OS X and Linux have established a presence on the x86 architecture. Design limitations and more compatibility issues. Although the IBM PC was designed for expandability, the designers could not anticipate the hardware developments of the 1980s, nor the size of the industry they would engender. To make things worse, IBM's choice of the Intel AT88 for the CPU introduced several limitations for developing software for the PC-compatible platform. For example, the AT88 processor only had a 20-bit memory addressing space. To expand PCs beyond 1 MB, Lotus, Intel, and Microsoft jointly created expanded memory, a bank switching scheme to allow more memory provided by add-in hardware, and accessed by a set of 4 16-kilobyte windows inside the 20-bit addressing. Later, Intel CPUs had larger address spaces and could directly address 16 megabytes or more, causing Microsoft to develop extended memory which did not require additional hardware. Expanded and extended memory have incompatible interfaces, so anyone writing software that used more than 1 megabyte had to provide for both systems for the greatest compatibility until MS-DOS began including M386, which simulated EMS memory using XMS memory. A protected mode OS can also be written for the 80286, but DOS application compatibility was more difficult than expected, not only because most DOS applications access the hardware directly, bypassing BIOS routines intended to ensure compatibility, but also that most BIOS requests were made by the first 32 interrupt vectors, which were marked as reserved for protected mode processor exceptions by Intel. Video cards suffered from their own incompatibilities. Once video cards advanced to SVGA, the standard for accessing them was no longer clear. At the time, PC programming used a memory model that had 64 kilobytes memory segments. The most common VGA graphics mode screen memory fit into a single memory segment. SVGA modes required more memory, so accessing the full screen memory was tricky. Each manufacturer developed their own methods of accessing the screen memory, even going so far as not to number the modes consistently. An attempt at creating a standard named VESA BIOS extensions was made, but not all manufacturers used it. When the 386 was introduced, again a protected mode OS could be written for it. This time, DOS compatibility was much easier because of virtual AT86 mode. Unfortunately, programs could not switch directly between them, so eventually, some new memory model APIs were developed, vCPI and DPMI, the latter becoming the most popular. Because of the great number of third-party adapters and no standard for them, programming the PC could be difficult. Professional developers would operate a large test suite of various known to be popular hardware combinations. Meanwhile, consumers were overwhelmed by the competing, incompatible standards and many different combinations of hardware on offer. To give them some idea of what sort of PC they would need to operate their software, the Multimedia PC standard was set during 1990. A PC that met the minimum MPC standard could be marketed with the MPC logo, giving consumers an easy-to-understand specification to look for. Software that could operate on the most minimally MPC-compliant PC would be guaranteed to operate on any MPC. The MPC Level 2 and MPC Level 3 standards were set later, but the term MPC-compliant never became popular. After MPC Level 3 during 1996, no further MPC standards were established. Challenges to Wintel domination. By the late 1990s, the success of Microsoft Windows had driven rival commercial operating systems into near extinction, and had ensured that the A-Euro-OE IBM PC Compatibility Euro computer was the dominant computing platform. This meant that if a developer made their software only for the Wintel platform, they would still be able to reach the vast majority of computer users. By the late 1980s, the only major competitor to Windows with more than a few percentage points of market share was Apple Incorporated's Macintosh. The Mac started out billed as the computer for the rest of us, But the Mac's high prices and closed architecture meant the DOS Windows onslaught quickly drove the Macintosh into an education and desktop publishing niche, from which it only emerged in the mid-2000s. By the mid-1990s the Mac's market share had dwindled to around 5% and introducing a new rival operating system had become too risky a commercial venture. Experience had shown that even if an operating system was technically superior to Windows, it would be a failure in the market. In 1989 Steve Jobs said of his new NeXT system, "It will either be the last new hardware platform to succeed, or the first to fail." 4 years later in 1993 NeXT announced it was ending production of the NeXT CUBE and porting NeXT STEP to Intel processors. Very early on in PC history, some companies introduced their own XT-compatible chipsets. For example, Chips and Technologies introduced their 82C100 XT controller which integrated and replaced 6 of the original XT circuits, one 8237 DMA controller, one 8253 interrupt timer, one 8255 parallel interface controller, one 8259 interrupt controller, one 8284 clock generator, and one 8288 bus controller. Similar non-Intel chipsets appeared for the AT compatibles, for example Opti's 82C206 or 82C495XLC which were found in many 486 and early Pentium systems. The x86 chipset market was very volatile though. In 1993, VLSI technology had become the dominant market player only to be virtually wiped out by Intel a year later. Intel has been the uncontested leader ever since. As the Intel platform gained dominance Intel gradually abandoned the practice of licensing its technologies to other chipset makers. In 2010 Intel was involved in litigation related to their refusal to license their processor bus and related technologies to other companies like NVIDIA. Companies such as AMD and Cyrix developed alternative CPUs that were functionally compatible with Intel's. Towards the end of the 1990s, AMD was taking an increasing share of the CPU market for PCs. AMD even ended up playing a significant role in directing the development of the x86 platform when its Athlon line of processors continued to develop the classic x86 architecture as Intel deviated with its netburst architecture for the Pentium 4 CPUs and the IA64 architecture for the Itanium set of server CPUs. AMD developed 64 Armenian DRAMs, the first major extension not created by Intel, which Intel later adopted as x86-64. During 2006 Intel began abandoning netburst with the release of their set of core processors that represented a development of the earlier Pentium 3. A major alternative to Intel domination is the rise of mobile computing since the early 2000s, which has been marked as the start of a post-PC era. Tablets and smartphones based on CPUs with the ARM architecture are especially prevalent. A version of Windows, Windows RT, exists for ARM-based computers. The IBM PC compatible today, the term IBM PC compatible is not commonly used presently because all current mainstream desktop and laptop computers are based on the PC architecture, and IBM no longer makes PCs. The competing hardware architectures have either been discontinued or, like the Amiga, have been relegated to niche, enthusiast markets. In the past, the most successful exception was Apple Incorporated's Macintosh platform, which used non-Intel processors from its inception. Although Macintosh was initially based on the Motorola 68000 family, then transitioned to the PowerPC architecture, Macintosh computers transitioned to Intel processors beginning in 2006. Today's Macintosh computers share the same system architecture as their Intel counterparts and can boot Microsoft Windows. The processor speed and memory capacity of modern PCs are many orders of magnitude greater than they were for the original IBM PC, and yet backwards compatibility has been largely maintained. A 32-bit operating system published during the 2000s can still operate many of the simpler programs written for the OS of the early 1980s without needing an emulator, though an emulator like DOSBox now has near-native functionality at full speed. Additionally, many modern PCs can still run DOS directly, although special options such as USB legacy mode and SATA to PATA emulation may need to be set in the BIOS setup utility. Computers using the extensible firmware interface might need to be set at legacy BIOS mode to be able to boot DOS. However, the BIOS EFI options in most mass-produced consumer-grade computers are very limited and cannot be configured to truly handle OSs such as the original variants of DOS. The recent spread of the x86-64 architecture has further distanced current computers and operating systems' internal similarity with the original IBM PC by introducing yet another processor mode with an instruction set modified for 64-bit addressing, but x86-64 capable processors also retain standard x86 compatibility. See also, AT, ATX form factor, Baby AT form factor, computer hardware, computer software, computing platform, custom-built PC, history of computing hardware, home-built computer, IBM personal computer, influence of the IBM PC on the personal computer market, PC speaker, personal computer, x86 architecture, MS-DOS, CP/M. References. External links, http://oldcomputers.net/compaq.html